The next type of coordinate system is the spherical coordinate system. For example, the point on the surface of the Earth, whose latitude is 40 degrees north of the equator and whose longitude is 80 degrees west of the prime meridian, is shown in this figure. Assuming that the Earth is spherical and has a radius of 4,000 miles, you would label this point using spherical coordinates, beginning with the radius, how far from the center of the Earth out to the point on the Earth. Negative 80 degrees, that would be 80 degrees from the clockwise from the prime meridian, and 50 degrees would be the angle from the North Pole down, 50 degrees. That is an example of you finding a location in space using spherical coordinates. A radius, an angle from the positive x-axis, and an angle from the positive z-axis. So in the spherical coordinate system, a point P in space is represented by an ordered triple. That first letter looks like a P, but it's a Greek letter rho, and it's rho, theta, and phi. Rho is the distance between the point P and the origin, and that rho should be greater than or equal to 0. It's a positive distance. Theta is the same angle that's used in cylindrical coordinates for a radius greater than 0. And phi, that's the Greek letter phi there, is the angle between the positive z-axis and the line segment OP, where O is the origin, from the origin to the point in space. And that angle phi should be an angle between 0 and pi. Note that the first and the third coordinates, rho and phi, are non-negative, and rho, again, is the lowercase Greek letter rho, and phi is the lowercase Greek letter phi. The relationship between rectangular and spherical coordinates is illustrated in this figure. To convert from one system to the other, you can use these conversion equations. Now, the theta is the same conversion equation if you're going from rectangular to cylindrical. The theta is the same as cylindrical. Now, the rho is the distance from the origin. So if you know the point x, y, z, the way you find the distance from the origin is using this equation. Rho squared equals x squared plus y squared plus z squared. That's using the distance formula. And tangent theta equals y over x. That's the same conversion equation. And then the way you find this angle phi is by taking the arc cosine of z divided by the rho, which is the square root of x squared plus y squared plus z squared. Now, to change coordinates between the cylindrical and spherical systems, you can use the following conversion equations. For example, if you're given a rho and a phi, you can use this first equation to find r. If you're given an angle phi and a rho, you can use this equation to find z, and so on. If you're given r and z, you can use this equation to find rho. And if you're given r and z, again, you can find this equation to find phi. The spherical coordinate system is useful primarily for surfaces in space that have a point or center of symmetry. For example, these surfaces have fairly simple spherical equations. A sphere centered at the origin with a radius c is represented in spherical coordinates with the equation rho equals c. If you were writing the equation of the sphere using rectangular coordinates, it would be x squared plus y squared plus z squared equals r squared. A vertical half plane is represented by the angle theta equals c, and a half cone is represented with the simple equation phi equals c, where c is some angle between 0 and pi over 2. For this example, we're going to find an equation in spherical coordinates for the surface represented by each of the rectangular equations. You can pause the video now and try these on your own and restart the video to check your answers. The first equation is x squared plus y squared equals z squared. Now to convert this to spherical, you're going to replace the x with rho sine phi cosine theta, replace y with rho sine phi sine theta, and replace z with rho cosine phi. And then when you square all of those, you get the equation, the following equation, that can then further be simplified if you factor out the common factor from the left side of the equation. You get rho squared sine squared phi equals rho squared cosine squared phi. If you divide both sides by the rho squared cosine squared phi, you get sine squared phi over cosine squared phi equals 1. Now that's assuming rho is not 0, so rho must be greater than 0. Now, using the trig identity, we get sine squared theta over cosine squared theta equals tangent squared theta. And tangent squared theta equals 1 when the angle theta is pi over 4 or 3 pi over 4. So the equation phi equals pi over 4 represents the upper half of the cone, and the equation phi equals 3 pi over 4 would represent the lower half of the cone. For part B, we want to take the equation and then replace the x squared plus y squared plus z squared with rho squared, and we're going to replace z with rho cosine phi. We get the following equation. Rho squared minus 4 rho cosine phi equals 0. And when you factor out the rho, you get rho times the factor rho minus 4 cosine phi equals 0. If you discard the possibility that rho equals 0, you have the spherical equation rho minus 4 cosine phi equals 0, or rho equals 4 cosine phi. Now the solution set for this equation includes a point in which p equals 0, so nothing is actually lost by discarding the factor rho, and the sphere represented by the equation rho equals 4 cosine phi is shown. So again, we start off with this rectangular equation, x squared plus y squared plus z squared minus 4z equals 0. By replacing the x squared plus y squared plus z squared with a rho squared, and converting the z, we get a simplified equation, rho equals 4 cosine phi. It may seem a little redundant to be able to express these in different systems, rectangular, spherical, or cylindrical, but when we get into doing some double integrals, triple integrals, whatever, we may find that it's more convenient to write it in spherical over rectangular or cylindrical. You may end up with much simpler integrals by using conversions.